So you're given this matrix, negative 0.8, negative 0.6, negative 0.6, 0.8. First of all, I asked you what the determinant was, and you said the determinant of this matrix was negative 1. And so that's just an observation to hang on to as you go forward. To find the eigenvalues, what did you do? Subtract lambda from the diagonal. Take the determinant, simplify it out. You had to do some FOIL there, but simplify it out, you get lambda squared minus 1 for the characteristic polynomial, and so the determinant equals 0 exactly when lambda is equal to either plus or minus 1. So there were your eigenvalues. Then to find a basis for each of the eigenspaces, you had to find the null space, the solution to the homogeneous equation for a minus 1 times I, so this is going to give you the lambda equals 1 eigenspace. Solving this homogeneous equation, which the second row disappears if you do the row reduction. In its parametric vector form, you can find out the basis vector of the solution set, negative 1/3, 1. We would call that an eigenvector. For the eigenvalue, lambda equals 1. And then likewise for lambda equals negative 1, you have A plus the identity. Set up that homogeneous equation. Its parametric vector solution has basis 3, 1. So there were your two eigenvectors for the two eigenvalues, respectively, 1 and negative 1. Then your picture takes those eigenvalue-eigenvector pairs, so lambda equals 1 and lambda equals minus 1, and sketches them out as the entire eigenspaces. So my question now is, what does this matrix do? This matrix, negative 0.8, negative 0.6, negative 0.6, 0.8, how does it act on the xy plane, given this information? So first of all, what is happening to vectors along the lambda equals 1 eigenspace? What's the difference between between x and ax? Well, yeah, that's maybe the difference between the two eigenspaces. But if I start with an eigenvector, if I start with a vector x, which is in this lambda equals 1 eigenspace, what happens when I apply the matrix A to it? What's it going to equal? Because it's in the lambda equals 1 eigenspace, ax is going to equal 1 times x. So what happens to those vectors when we hit them with A? Nothing. Lambda equals 1 is what we call the fixed eigenspace. In other words, every point or every vector that starts in that line is going to stay exactly where it is when A acts on it, because ax is equal to 1 times x for vectors x that lie in that eigenspace. So everything in that, everything along that line stays exactly where it started after A is applied to it. What about the other line? Yeah, along the other line, the lambda equals negative 1 eigenspace, if I take a point in this line and I apply A to it, ax is going to equal minus 1 times x, and minus x is going to be the opposite. So one of the ways of visualizing what this transformation is doing is by, let's just take let's suppose that I just came into the xy plane and I chose a whole bunch of points, and then maybe I made them into a picture of the letter R or something like that. What's going to happen to this letter R when I apply the matrix A to every one of its points? Well, everything in this direction is going to remain the same. Everything in this direction is going to trade places. It's going to reflect. So all in all, what's going to happen to that R when I apply the matrix A to it? It's going to become the last letter in the Russian alphabet, backwards R. So what we can say is that our matrix A exactly represents reflection. And it's reflection through what line? What's our axis of symmetry for this reflection?
Lambda equals 1.
Right, the lambda equals 1 eigenspace. Because it's the axis of symmetry, everything stays the same on that line. And it happens that because our line is spanned by this vector, we can say it has the equation y equals minus 3x, if you like. So that's what this linear transformation described by this matrix is doing. This transformation is exactly reflection through the line y equals minus 3x. But we didn't know that until we determined what its eigenvalues and eigenvectors were. Having eigenvalues of only plus and minus 1 is what makes it a reflection. That negative 1 tells us the direction that's being reflected. The 1 tells us the direction that's staying the same. Also notice what relationship these eigenspaces have to one another. How are they related together? Actually perpendicular. That doesn't always happen with eigenspaces, but it did happen for these eigenspaces. And it was part of what made this a reflection. In any reflection, you have to go perpendicularly, directly across the fixed space. And so it was only the eigenvector-eigenvalue analysis that told us that. Also, we didn't get to this yet, but we'll see next time the relationship between the determinant of a matrix and its eigenvalues. There's a very simple bit of arithmetic that relates those together.